Welcome everyone to this keynote lecture for this IEEE TSP 2022 conference. My name is Athanasios Tsanas and I'm based at the University of Edinburgh in the UK. Today, for this keynote lecture, I'm going to be talking to you about work on revolutionizing contemporary healthcare. And the way we propose we achieve that is on the basis of capitalizing on multimodal data and, of course, ubiquitous devices that are increasingly affordable and accessible. I'm talking about smartphones, wearable devices, applications that many of us are using. And as a subtitle, I've included the precision medicine approach, because ultimately, each one of us as a patient, we care about how things would work down to the single individual, down to us. Let me start with a confession. I have diagnosed COVID positive yesterday, and as I was preparing this talk, I was thinking it is really the case that when you have a disease, you really want to identify tools and approaches that clinicians can treat you down to the single individual. So, no disrespect, but having a disease, in this case COVID for me, what I really care is how can we find the best way that actually I can be treated. And I think this is the case with all patients across all diseases. So my talk today is about how we can try to develop tools that actually can facilitate this personalized approach through the use of different equipment. So one of the key things you have to understand is when it comes to medication, one size really doesn't fit all. So in fact, for every single person that certain drugs can actually be beneficial, that same drug fails to deliver and improve the conditions for a large proportion of the population. So for every single person that these drugs actually help, there are 3 to 24 people that these drugs do not help. And in fact, if you go and think about statins and certain types of other medications, that percentage is higher. Clearly, certain drugs work extremely well for some individuals, but they fail to generalize for others. It's the same thing with COVID. We have seen it over the last 2 years. There are certain treatments and medications that work for some, and different people have different symptoms compared to others. So what can we do to actually identify and develop more personalized approaches to help down each individual? Quite interesting, there is this call for one-person trials. It was published in Nature in 2015. It is a very interesting concept. It's about the idea that you have a single individual that you monitor very thoroughly with lots of different devices, perhaps, or lots of different modalities. So this is where the multimodal component comes in. And you try to identify for that individual what is happening and how they're going to respond to therapeutic interventions. So it is, I believe, the time that we should be moving from the average and what could potentially be working for some people down to developing tools that can help each individual person, or at least develop tools that can be more personalized, at least working with maybe a subset of individuals where we identify certain characteristics that could be helping that particular group. So when we think about precision medicine, one of the key things you might be thinking is the omics category. And of course, I'm not a biologist or a clinician, so I'm not really qualified to talk about this very interesting aspect for how you can develop tools and penetrate even at the molecular level. So develop, for example, techniques to focus on genetics. Many of you would be aware of genome-wide association studies. We know that even for COVID, there were related studies that try to identify what is happening down to the DNA of individuals. The second big category that we can try to think of developing tools towards precision medicine is continuous assessment. And that can be achieved using self-reported outcome measures. And many of you may have come across the term patient-reported outcome measures, or PROMs. And then also developing tools on the basis of sensors. For example, using wearables and smartphones that probably most of you already have. The other concept is what I mentioned in my previous slide of having N of 1 trials, which basically means you have a very thorough investigation of that individual for a long time to try to identify what really works for that person. And in the meantime, you can try to adjust the way that they behave and the way they perform in terms of certain medication or treatment and rehabilitation. And ultimately, for that individual, you need to monitor outcomes and identify what really works well. Now, of course, for that last part, you have to really do it for a couple of individuals to be able to identify what might be something that we could potentially generalize. But it is one of those interesting thoughts of developing tools towards precision medicine. Now, my talk today is going to be focusing on the continuous assessment. So how can we focus on getting information from people's self-reports? And we have some challenges because we do not always get those self-reports in time, or in some cases we might have missing data, how you can compare those self-reports between individuals. And then a large part of my talk is about capitalizing on resources that are nowadays increasingly available in the form of smartphones and wearables. I thought before we go down to a couple of examples, it would be quite useful to understand what is really happening under the bonnet. Many of us drive. We don't necessarily need to understand exactly how the car operates, but it is really useful before we get to the analytics and try to get an understanding of the problems and how things operate, that to have at least an eagle's eye view, an overall idea of how things operate. And that's why I say, let's have a look under the bonnet. So the first step with most problems that we have, at least in healthcare, but this can be generalized across different domains, is that you have the raw data, which can be in structured or unstructured format. For example, in healthcare, we frequently have physiological signals like the electrocardiogram, the electroencephalogram, voice, and so on, lots of different examples. You may want to monitor someone's physical activity, and I guess many of you may be wearing certain trackers that will tell you the number of steps, an estimate of the calories, and so on. Another example could be assessing someone's location, in particular the trajectory someone is following, because that can have lots of interesting information and valuable information towards assessment of some outcome. So what we try to achieve typically is apply some algorithms to get the raw data, the raw information that you have in these original data modalities into what we call the design matrix. So the design matrix basically comprises of a number of features. Let's say you have M features or characteristics and N samples. So the N is the number of participants you have in the study, or the number of samples you have in the study. And you have characterized each of those individuals across a range of characteristics. And these can be, for example, demographics. It could be additional information you can get from processing different modalities. Ultimately, what you try to achieve is get all this multimodal information, potentially from lots of different raw data modalities, and present it conveniently into this design matrix. Now, the key thing, of course, is that you will have to apply a lot of signal processing, time series, image processing, video processing algorithms, depending on the type of raw data you have in the first place. And when you apply these algorithms, and you can think of your favorite Fourier transforms or whatever algorithms you might want to apply to the raw data to extract features, by applying these algorithms, every time you will be getting some scalar values to characterize what's happening for that individual. Now, the key thing, once you have extracted the data and you have managed to put things into that convenient design matrix, is when the ML component comes in. So the first part is where you generated some features from the raw data. And the second part is about selecting or transforming the original features to get either a subset of the original features or get some transformed features, some features that hopefully will be more informative of the outcome. And the last part is the statistical mapping. So it is about finding ways to associate the information you have in X with Y. So let me reiterate, you have N samples, you have M characteristics for that problem, you have the outcome that is typically provided by the experts of that domain, or it can be otherwise measured. And ultimately, what you try to do is get this design metrics thoroughly populated with your demographics, genes, whatever features you have extracted. And then the ML part, which is finding a functional form to associate the information in the design matrix with the outcome of interest. It is very useful to think of problems in that way because this framework is really generalizable. It can be applied across any domain, really. You can think of extracting features and populating the design matrix from finance to healthcare to any application, really. And then this part, the statistical learning, the statistical mapping part, is really where all your favorite logistic regression, linear regression, random forest, SVMs comes in. Ultimately, finding ways to associate the information to map the information from X and predict this estimated Y. Now, let me get down to specific examples. And the first one is, I want to make a case for patient-reported outcome measures. So crucially, it is very important to understand how each individual feels. In many domains, you may have a clinical opinion, which is nothing more than a clinical impression of someone's symptoms. But at the end of the day, if you think about it, what that specific individual cares about is how they themselves feel. So if they're doing worse across some clinical scale, but they feel better, I guess most patients would be happy to take that up. It is not really useful to say that on a clinical scale you're doing better if you're actually yourself feeling worse. So the first key thing is it is quite useful to be getting these patient-reported outcome measures by eliciting responses from individuals. One of the things we have to appreciate is that many times with the classical current assessments, we cannot really understand what's happening with individuals. So we can get these patient-reported outcome measures when people come into the clinic. So they have to be physically coming in, they may need to take some time off work, or perhaps their carers take some time off work. And then the clinicians ask those patients to understand what was happening between perhaps interim assessments, or what happened between the time that they were healthy and now they feel they have certain symptoms of a disease. For example, in a lot of the work I'm doing with neurodegenerative disorders and mental disorders, clinicians get to see patients once every 6 to 12 months. And then they ask them, for example, if they were anxious or if they slept well 3 months ago, and then how they slept 4 months ago, and so on. Long story short, this clearly introduces recall bias. I don't know if you're like me, but if someone were to ask me if I was really stressed or really happy or really annoyed, maybe a month or 2 months ago, probably I would not have a very accurate recollection, particularly if someone were to ask me to provide very fine resolution, like if there was a specific week in, let's say, June or May or April that I was feeling bad, or perhaps I didn't sleep well. Most people, I think, would have trouble to pin down what was happening on a week-by-week basis if they had to think about what happened in the last 6 months. The other thing that you have to be aware is that, of course, all those self-reports are subjective. And I'm saying that in the sense that if someone were to ask me, for example, how stressed I am in a scale, let's say between 0 and 10, and I say 3, and someone were to ask you the same question and you also responded 3, that doesn't necessarily mean that to an outsider, if there was some objective way to assess that, those 2 3s that both I and you have said is really equivalent. So that is one of the crucial things we have to be aware with PACE reported outcome measures. Often, the critical aspect there is observing changes in those longitudinal responses. So it is quite crucial that we identify and develop tools that can collect longitudinal responses to those PACE reported outcome measures. The other thing to keep in mind is that with many of these disorders, frequently it is quite difficult to objectively assess interventions. And I refer particularly to the domains I'm working on in mental health, neurodegenerative disorders. Frequently you have experts disagreeing with each other. This is what we call the inter-rater variability. And increasingly, for example, some firms might not be willing to reimburse clinical experts for the treatment for certain individuals. For example, insurance companies, they might not be willing to reimburse a psychologist or a psychiatrist because it's very difficult to objectively demonstrate if their treatment had a beneficial effect down to this individual. So let me tell you about a project that we have completed a couple of years ago. So this is the activity monitoring of symptom severity project. And basically that project monitored 48 people with bipolar disorder, 31 people with borderline personality disorder, and as a benchmark, we had 51 healthy controls. And what we asked people to do is complete a range of questionnaires. So the first one, and you're going to see this in the next couple of slides, the first one is quantifying manic symptoms. The second one is about depression. The third one is about anxiety. And the fourth one is a novel questionnaire that we validate in our study. Now, the crucial thing there is that we collected data for a full year for the vast majority of participants. And for the first 3 questionnaires, we got it on a weekly basis. The last one was on a daily basis. So that is really big data that we can really dig in and try to understand what is happening in terms of what people self-report about how they feel for a full year on a daily basis. So the way we achieve that is with a smartphone app that we had developed when I was still based at the University of Oxford. So essentially what we did is use established questionnaires and the new questionnaire that we have developed, which was actually very simple to elicit and fit it on a single page of or a single screen of the smartphone. So we wanted to ensure that this was something that would not be burdensome for participants and people could complete it within probably 20 to 30 seconds. The crucial thing that we reported is that we managed to demonstrate we had more than 80% adherence, and that is key. If you really are trying to make a difference and try to demonstrate things work well with patient-reported outcome measures, you really want to ensure that you get those adherence metrics, those responses coming in quite regularly throughout the term of the study. So in our study, we managed to collect data from those 3 cohorts, and you can see that even towards the end, we still have managed to observe that we have about 80% adherence for every single group. That is crucial for us to understand what is happening on a day-to-day basis for individuals longitudinally. And this was the first paper we published in this domain, basically reporting those changes long term. The second thing we try to assess is, following those self-responses, we try to objectively understand if people were, for example, manic. And the way that this is done is, you see, we have an individual to model for a full year. What we try to achieve here is understand on the basis of the responses if those people were above certain thresholds. And if they were above certain thresholds, you can see with the transparent red color here that those participants were actually manic. And the crucial thing is that you can actually do this almost on a day-to-day basis. So you almost have real-time information about what is happening with individuals on the basis of those responses. So the second questionnaire is if you were depressed. So once again, you have the self-response of individuals. You can see I've marked with X every time they provide the response. So here, for example, you can see they didn't provide the response for that particular week. And if they're again above a threshold, then that indicates they were depressed. Now, as I said, the first couple of questionnaires were on a weekly basis. The last questionnaire that we proposed in our study, which we called Mood Zoom, is actually on a daily basis. And you can see that on the daily based variability, we can get a lot of interesting understanding of what's happening with mood fluctuations throughout the participant's life longitudinally on the basis of the daily, day-to-day variability of what they self-report. I'm going to revisit this project with mental health in a bit. I want to switch gears and try to move on to an argument for using sensor-based assessments. So many of you would be aware that smartphones and the smartphone market is booming. In fact, I would probably have a very good educated guess that pretty much every one of you has a smartphone, or at least the very vast majority. A couple of years ago, maybe people over the age of 70, they would not own a smartphone. Back then, if you think about it, 10 years ago, smartphones were probably more expensive, although of course we still have quite expensive smartphones, but you didn't have the low end of the spectrum where basically some of the smartphones are actually affordable. And also, many people at those age ranges, they were not accustomed to the use of technology. Nowadays, most 55 to 75-year-olds actually own a smartphone. And as the years roll on, we expect more and more in those late stages of life would actually be very competent and comfortable using smartphones. That is crucial because that means that people can use the smartphones both to respond and say how they self-assess their symptoms. So that goes back to prompts, and also use the sensors of the smartphones to assess what is happening with their condition. In terms of the wearables, I don't know how many of you actually own a wearable and you like to measure your own steps or activities and so on. Myself, I'm a very keen person. I'm actually having 2 wearable devices. The reason I'm doing that is because I like comparing different brands and trying to see what information I can get from different devices as part of my research. But the key thing is that the wearables market is really booming. So it is estimated that there were more than 20 billion spent in 2021 in wearables, and that figure is expected to rise to more than 70 billion by 2026. So these are staggering figures, and basically what they indicate is that there is appetite and an increasing understanding of the values of wearables, many of them increasingly affordable these days, and we can expect a further rise in their use across the population. And of course, that will pervade the older group that we know that they may have certain healthcare needs. Now let's talk about the smartphones in healthcare. How can actually use a smartphone to help towards the assessment of someone's different conditions? One of the projects we did last year was, and this is a project we've done with colleagues in Harvard, the Harvard Medical School, was basically using iPhones and recording someone's physical activity in the sense of steps. iPhones have this capability, and they are part of the health kit, where basically you can get this general activity. And the key thing is that you can try to match that with metabolic equivalence of tasks. So what we demonstrated is that we can try to monitor people long-term who have iPhones in their pockets and they walk freely, and match that information we can extract longitudinally with a single visit that they do, for example, during a stress test. Now, the stress test is this example where you go and you run on a treadmill, and the clinicians perform a series of measurements, for example, measuring the heart rate, the blood pressure, and try to see what is happening in terms of exercise, both as your heart rate increases and then as you recover, how things improve when you return back to the steady state at rest. So that is a measure of the cardiorespiratory function, and it indicates basically, is a very good indicator of healthcare status in terms of the cardiovascular system. And what we managed to demonstrate in this study is that the information we get from the smartphones recording activity can actually be matched very well to the metabolic equivalence we can get through a stress test in clinic. In practice, that means that someone can be using this device, can be collecting data on the go, and will have a very good understanding of the day-to-day status in terms of the cardiovascular system. Let me switch gears and talk about a different application. And this one focuses on the smartphone again, but this time we're going to discuss the geolocation. Now, this might seem counterintuitive, or perhaps even you might be opposing the idea of recording geolocation, and you'd be right that there are some valid reasons for potentially this data being quite intrusive. For example, you wouldn't want someone to know your exact geolocation at every single time. However, from a healthcare perspective, we have demonstrated this can have great benefits in terms of assessing if someone is, for example, depressed. So what we did is we collected data. This goes back on the mental health project that I discussed earlier. So we collected data and we identified the place where they spend most of the time at home. So most of the time during nights, which we assigned it to be home. Although you'd be quite surprised with 25 to 30-year-olds if they might be moving in different places during the night. But generally speaking, the place where they spend most of the time at night, that is what we assessed as home. And then we extracted a lot of different characteristics to indicate the patterns of their movement. And the great thing there is that we can map the patterns of their movement on the QIDS score, which indicates depression. Practically, that means that you just have your phone with you. It records the geolocation every couple of minutes, every 5 minutes. And then on the basis of those patterns, in terms of the movement that someone has, this can identify, I think it was about 83% accuracy, if someone has depression for that week. Now, it is very difficult to exaggerate and understand really these implications of that finding. It basically means that someone doesn't have to wait for 6 to 12 months to see the clinician. Instead, the clinician can be presented almost real-time data, where every couple of weeks they get to see the patients if they were actually depressed over that last week or two. And if certain individuals have been very depressed, maybe those clinicians can bring the patients earlier in. The key thing is that this is a personalized approach. So we target each individual where we get the data. This was started published in TBME in 2017, and as I said, it is quite crucial that we try to capitalize on this kind of information that we have shown that geolocation can really be predictive of a condition like depression. Let me move on with a different topic, and for now we're going to switch gears and move on from wearable devices, from smartphones to wearable devices. So we work with a device called the Proteus patch, and basically this is a patch that you put on your chest and it records heart rate variability. So what we want to do is try to assess if this intrinsic circadian variability we might have in terms of temperature and heart rate, if this is actually related to mood changes. And this builds on the findings we said before on the mental health project, where we had data from the patient-reported outcome measures, data from the smartphones, and now data from different wearable sensors too. But what we managed to demonstrate is that indeed, on the basis of monitoring heart rate and temperature, we can actually understand what is happening in terms of the diurnal rhythms and the mood variability. Now, that is quite important if you think about it. All of us will have some mood fluctuations during the day. Just imagine a case where, I guess for most of us as academics, you have a grant rejected or a paper accepted. Suddenly you have a very large mood swing, maybe you went down or up. So for most of us, we really intuitively can understand that this is what happens. We have those mood swings. Now, particularly people with mental disorders, they have those mood swings much more regularly. And the key thing here is that monitoring these different modalities, we can actually understand what is happening within those mood transitions, this mood variability during the day for those individuals on the basis of collecting the objective data with sensors. I should probably say that the way we try to manage to map that is that people were providing self-responses up to 10 times a day. So we managed to do it on a personalized level down to each individual, where we try to see those changes in the heart rate variability and the mood fluctuations. The next wearable sensor I want to talk to you about is this smartwatch I'm wearing myself. This is the Genie Active, and it is one of the devices that can actually provide raw data. So many of you would be probably familiar with Fitbits and Garmin watches and other consumer level devices. And these are great because they can provide very intuitive frameworks and an app on a phone that people can actually see and engage with their data patterns. However, as researchers, it is crucial that we get access to the raw data. And in that sense, this is one of the devices. As far as I know, there are probably 3 or 4 smartwatches that provide access to the raw data. The key thing is that we develop the algorithms to map the original hexadecimal format down to some processed patterns where we identify activity and sleep. We extract features and we characterize the data of each individual on a day-to-day basis, and then we can use that to map onto the longitudinal outcomes of interest. So one of the key things we have done was actually compare the state-of-the-art accuracy in terms of published algorithms in the literature and the accuracy we can get in terms of the new algorithms we have proposed. So this is some work we published in 2020, and what we demonstrated is that we can get the onset and offset extremely accurate, particularly for healthy controls, and then we could get it fairly accurately for people with specific types of different disorders. For example, here we had people who had experienced some traumatic event and people who actually developed a post-traumatic stress disorder. And if you're not aware, post-traumatic stress disorder, one of the hallmarks symptoms of the disease is disturbed sleep. So what we managed to demonstrate is that we can do very accurately even in that case, whereas the state-of-the-art algorithms do not generalize well in pathological cases. So let's move on beyond that. I mean, assessing sleep is a useful prerequisite and a useful input to have, but it's not the full story. We need to move beyond that. So what we extracted is what we call the actogram. This is a very classical way that circadian biologists like to see data. Effectively, what an actogram is like a 48-hour day. So if you think this is the Friday, 4th July until this point, that's midnight. And here is where Saturday, 5th of July starts. And then the Saturday, 5th July, the second part of the graph, is repeated on the next half over here. And again, you have Sunday. So basically, the second half of the graph is repeated as part of the first part of the graph for successive plots. And the reason that circadian biologists and psychologists are quite keen on this representation is because they can see what is happening around midnight. So you can see here, for example, that the algorithm has identified with green, established here, that this person went to bed a little before 12 o'clock. So we have developed all these algorithms, as I mentioned previously, and we map it here with green. The blue is the activity. The green indicates if the algorithm believes that this person has been sleeping. And with this transparent red, we have the time that someone was detected as not wearing the device. So that can be quite useful information as well, because we do not want to be processing data where people do not wear a device. Now, the key thing there is that we can try to extract information from someone wearing the device and then mapping it onto the self-reported outcome measures. So you can actually obtain differences and see what is happening when someone is manic and when someone is depressed. So you can extract features and you can actually try to map it onto the basis of the self-reported outcome measures. That is key because practically it means that someone can wear a smartwatch, and on the basis of the smartwatch, you can identify aspects of their mood variability. Another project in terms of the post-traumatic stress disorder, as I mentioned previously, one of the key challenges we have, and something that the insurance companies are not comfortable with currently, is that they might have some reservations in terms of paying experts for treatment that cannot be easily quantified. So as far as we know, we're the first group to objectively demonstrate what is happening before and after. So you can see this was before treatment, before cognitive behavioral therapy treatment, and after, and you can see that the patterns were actually quite broken. The sleep was not continuous, or actually quite varied, whereas after treatment, this individual was actually sleeping much better, longer, and so on. And that can be reflected on the features we have computed. So this provides a very useful, meaningful way of actually objectively assessing if an individual is doing better following treatment. So we are quite excited about this finding because it indicates that for the first time, we may have objective ways to assess longitudinally changes after therapies for neurodegenerative and mental disorders. In a different application, again, staying in the area with the smartwatch, we focused on stroke patients, and in that case, we had differential treatment. So what we want to do here, excuse me, was try to assess if this differential treatment and the self-reports in terms of, for example, people referring in terms of their anxiety and their fear, if this is actually reflected in also the data we get from the smartwatch. And indeed, we have managed to demonstrate that there is some matching. We had only 27 participants, so that study was really a proof of concept. We cannot claim anything causative, and all the findings are quite tentative with such small participant cohort. However, it seems that there is some promise in terms of using the device also to assess for differential treatment. The last broad topic I want to discuss with you today is about the use of speech. It is a large part of my research work for how you can use speech signals And I would argue it is really an underutilized source of information. We can really use speech for a range of assessments and use it in healthcare. So a large part of my work is on using voice signals or speech and neurodegenerative disorders like Parkinson's. So let's talk about the first project we have done a couple of years ago now. So the first topic is trying to see if you can differentiate controls and people who have been diagnosed with Parkinson's early on. Now, if you remember, with many of these disorders, it is actually quite difficult to diagnose early, and clinicians might actually differ in their assessments. So it is quite important if you can provide them with a decision support tool. So what we demonstrate here is we got data from the NCVS, which is the leading institute in the world, the National Center for Voice and Speech in the States, and we managed to demonstrate that we can differentiate those two groups extremely accurately. In fact, we can differentiate controls with Parkinson's with more than 98.6% accuracy. This is wonderful. Of course, I'm not going to claim that this is diagnosis, because we have to be very clear here that this is only differentiating two groups. So it's a binary classification problem, and the extent of my claim is that we can differentiate very accurately people who have Parkinson's from healthy controls when you have high quality speech data. And I'll emphasize the high quality aspect because we're going to revisit it in a bit. So quite inspired by those findings, we said, let's try to democratize access. Let's try to get these outputs to be widely used. So instead of having only about 40 participants we had previously, let's try to collect data across the globe. So in fact, we ran the Parkinson's Voice Initiative where we collected data from more than 10,000 individuals. We got about 2 phonations per person. So that's why we got 19,000 phonations. And these were collected across 7 geographical locations. The data was quite imbalanced. About 10% of those recordings were from people with Parkinson's, but this is still very useful. This is the largest speech Parkinson's database. Now, the problem with this study is that we had to rely on people's own smartphones and or perhaps landlines, and this great variability in networks, and the sampling frequency was down to 8 kilohertz. So we no longer have the high quality data we described in the previous project. And that is why, in some higher sense, this project was not as successful as we would have wanted. So we could not replicate this 98% accuracy. In fact, we struggled to get 70% differentiation accuracy between controls and people with Parkinson's on a balanced data set. And the reason we believe this is happening is because of the data quality issues, the use of the 8 kilohertz, and the fact that there is great variability in terms of the networks that were used across different countries, different devices, different microphones, and so on. However, the Parkinson's Voice Initiative was great in the sense that we could try to ask different questions that would not otherwise be easy to ask. And one of these is finding ways for assessing Parkinson's subtypes. So you may know that a lot of disorders, for example, like asthma and Parkinson's and so on, they really act as umbrella terms. What that means is that although people are given the same diagnosis, you have Parkinson's, you have COVID and so on, in fact, we know that these affect people differently. Therefore, we can term those as umbrella terms, that basically all these different subtypes, indeed, they are classified as single disease, but probably they should be like subtypes or different, almost like different diseases. So the key question that we wanted to ask, and given that we have the largest speech Parkinson's database in the world by far, is the first time we can actually answer this question effectively, is if we can define useful Parkinson's subtypes just on the basis of using voice signals. And the answer is yes, we can. So you can see here we have the Boston data. This is one of the 7 geographical locations we collect data. And this is the silhouette plot. So basically, anything above 0 indicates our confidence in samples being selected as part of a specific cluster. Anything below 0 indicates that we're not confident in the samples belonging in that cluster. So you can see that for the vast majority, we developed the algorithm, we identified 4 clusters. And for the vast majority of samples, we can be very confident of the presence of those 4 clusters. We try to visualize data with a data projection technique that many of you would probably be aware of, the T-distributed stochastic nearest stochastic neighbor embedding, which basically tries to project data from the high-dimensional space down to a 2-dimensional space. And you can see that the samples are actually very nicely summarized in 2-dimensional space, and they're grouped together. So look at this cluster. Very nicely situated, everything seems to be together. So I should emphasize that these are independent. So the colors that you see here and the projections are actually completely independent. So TSNE does not work with labels. It operates directly on the data and finding a 2-dimensional projection of the data. And the colors is something we included later on the basis of the labels. And the labels in that case are the cluster outputs. Now, granted, those individuals here, they should have been ideally close to these ones. So granted, for that cluster, we might have some discrepancy. However, for the other 3 clusters, you can see it is a very clear differentiation when you have things in the projected space. Apologies for that, COVID is kicking in. Then, of course, we want to move further. We want to demonstrate that what we have is really meaningful and results can be really generalized across cohorts. So we want to basically externally validate our findings with the other geographical locations. So I'm presenting you data from our Canadian friends, and you can see that we have the 4 clusters and they're very nicely separated. You have some very few samples that are actually not very confident if they belong in the right cluster as they were assigned. And once again, when you have the projection, you can see how nicely they're separated. This small group of individuals being in this cluster over here corresponds to this small cluster over here. We have very few samples, but all of them are very nicely clustered and very nicely belonging to that cluster. So again, it is very difficult to underestimate the implications of that. It basically means that someone can stay at home, provide sustained vowel phonations, and the findings will generalize well. We trained using the hyperparameters and everything on the Boston cohort, and things generalized out of sample, completely external validation on the Toronto cohort. And things generalized similarly very well in the Oxford cohort that you can see. So once again, the clusters are fairly well separated. Here we have some perhaps differences that you can probably observe here that we're not certain about the membership of those clusters. So this was something we published in Nature Computer Science earlier this year. Let's move on to Parkinson's telemonitoring. So someone has been diagnosed with Parkinson's. How can we actually try to assess the symptom severity? So once again, we can apply signal processing algorithms. We can monitor their symptoms on a week-to-week basis. So what you can see here is that we monitor someone, we monitored actually 42 people with Parkinson's on a week-by-week basis for 6 months. They were not medicated, and what we demonstrated is that we can replicate very well the symptom severity. So let me put this into context. So the black dots is the clinician's estimates of the symptom severity metric, which is called UPDRS. Let's not go into too much detail. And the red is actually the probabilistic estimates of my algorithm. So if we're doing well, as you can see here, most of the time the red probabilistic estimates would coincide almost perfectly with the dots. Granted, in some weeks, like here, I might be 10 UPDRS points away, but for the vast majority, we're very accurate. Now, I know that many of you would not be aware of this clinical metric. I should probably say that it spans the range of 0 to 176. 0 is healthy, 176 is someone who's vegetable. And two trained experts might differ by about 5 UPDRS points. So extremely important finding. You can use voice and actually replicate this clinical metric of the extent of Parkinson's disease symptoms, and you can actually do it much better than the inter-rater variability, the agreement that two experts might have when they blinded to each other's assessments. I should probably say that the previous study was done with a device that was commercialized by Intel. And this was great, but what I was thinking is it would be quite useful if we can try to democratize access to this technology, particularly nowadays that people are increasingly using smartphones. So I developed a fairly comprehensive framework for how you can encode and decode the data that you can basically embed as part of a smartphone app. And the reason we're doing that is because we want to avoid effects that may be happening in the communication channel. So you can imagine that someone is in a village where maybe the signal is not very good. You can imagine that this is a stormy night. So basically, the problem is that the signal might be corrupted with noise and might not be very accurate. So following this communications protocol, we can recover the signal extremely well. Now, the microphones in your phone are probably about 60 dB in terms of the signal to noise ratio. And what we demonstrate here is that even if you go down to 10 dB, as we said in a noisy night or something, you would lose very few bytes or other bits here. So what you can see here effectively is that you would have almost 1 to the 10 of the power of 5, that 1 bit is actually wrongly transmitted. Practically, that means that you can actually very accurately recover the signal in the receiver. You can apply your algorithms, and what we demonstrated is that we can replicate the UPDRS with amazing accuracy again, less than 3.5 points from the ground truth. Granted, it's not as accurate as the previous one, but it is extremely promising. This was something we published last year in 2021. And then we'll push things further, where we basically try to see if we can assist experts towards earlier diagnosis. So what can we do to help experts capitalize on voice data, which we collect from smartphones, to actually assist neurologists to make a clinical assessment of Parkinson's as early as possible. Now, granted, we do not have enough samples, but it is a work in progress where we're collecting more and more data that we can retrospectively visit and try to see if there was some cue on those people who are currently at risk, and some of them may develop Parkinson's. What can we do to actually retrospectively revisit the data and try to assist experts make those assessments earlier? And the reason we want to do that is because the earlier you assess Parkinson's, the earlier you can intervene and provide a much better quality of life for that individual. If I can try to summarize, I know I've covered a lot of different areas, but I hope I've managed to convey my excitement about this area, about the technological advances and the unprecedented opportunities that we really have these days. We talked about capitalizing on patient-reported outcome measures, which back in the day, maybe 20 years ago, was on a paper-based format. Nowadays, increasingly, they are part of embedded smartphone apps. Of course, the key thing is that many of these devices and many of these patient-reported outcome measures can convey clinically useful information. And I hope I have made a convincing argument for how you can use different devices and different self-reports to actually monitor symptoms across different disorders. Generally speaking, there is a move towards collecting passively collected data. So ideally, we want to perhaps put on a device and forget about it. It's not very convenient if someone actively has to change something all the time. It is much better if they have a device and that device provides data and some insights. And I think that is where the field is moving, with all the different devices we discussed so far and trying to get passively collected data. I would like to leave you with a quote that I really like from Barack Obama. We have all been talking about change and hoping that things will improve in the future. I think a lot of the work that we have covered so far encapsulates this very well. We are the change we have been waiting for, and collectively as a community, we should be striving to work, collaborate, work across disciplines, and deliver useful tools and techniques that will truly revolutionize healthcare. With that, I would like to thank you. I should probably say there is data and code available in my research group website. I want to acknowledge a lot of people that have helped me along my journey with papers and sharing resources and advice along the years. If you have any questions or you have any thoughts, you want to discuss anything, by all means, feel free to approach me. I have my email on the first page of this presentation.